Good evening. My name is Carina, and the title of this presentation is Further Insights of the Non-Bragg Scattering Impact on Internal Wave Signatures in Full-Polarized L-band SAR Imagery. So, the internal waves propagate along the pycnocline in the ocean, generating convergence and divergence current surface. And the current surface model the sea surface roughness. So the internal waves appears typically in SAR image as alternating and periodically dark and bright bands like here. So the bright bands are related to rougher surface and to convergence current zones. And the dark bands are related to smoother surface and divergence current zones. So, the internal waves cause modifications on the sea surface current, and the sea surface current model the Bragg waves. Okay, and so this theory can explain fairly well the internal wave signatures on SAR imagery. However, this theory fails in explaining some points. For example, this theory fails in explaining the strong signatures that can be found at C and X band caused by internal waves. So this means that this theory should be improved. And some authors has been working in add the contribution of the breaking waves. So here in this picture, we have an internal wave that is propagating on the ocean. And here we can see, for example, the whole section followed by the smooth section and followed again by a half section. Okay, and in this second half section, we can see some evidences of breaking waves in the sea surface in a lot of places. So this study aims at analyzing the scattering mechanisms associated to polarimetric SAR imaging of internal waves by considering multipolarization backscattering coefficients and also second-order descriptors. And this is important because the understanding of SAR signatures of internal waves should be the basis for developing advanced scattering models that may improve the generation of added value products and the retrieval of metocean geophysical parameters. So, in order to understand the normalized radar cross-section that comes from the non-polarized scattering, we can consider first the total normalized radar cross-section as the sum of two terms. So the first terms, this one is related, the first one is related to the copolarized two-scale Bragg-like surface scattering coefficient, and the second one to the non-polarized scattering coefficient due to the breaking waves. And so using, in order to extract the contribution of the non-polarized scattering, we can use this equation here and this equation can be solved considering the polarization difference between the copolarized channels, that is the sigma VV minus the sigma HH, and also considering this particle here, the PB, where the PB is the two-scale Bragg scattering copolarization ratio, which is mainly ruled by local geometry and tilting effects of the surface, the scattering surface. So our data set is composed by 10 L-band ALUS pulsar imagery acquired in a polarimetric mode, and all images were acquired in places where the presence of internal waves are well known in literature. For example, in the Galapagos Islands and in the Flores Sea. And the wind information was extracted using the reanalysis data from the NCEP model. So in the first experiment, in order to do the first experiment, we have done transects perpendicular to the internal wave traveling direction. Okay, like here in this figure. And we did a transect for each image of our data set. And for each pixel of each transect, we have splitted the pixels in two different classes. Okay, the first class is related to the internal wave crests, and the second class is related to the internal wave troughs, where the internal wave crests are related to the rougher surface and the internal wave troughs to the smoother surface. Okay, and so we have computed the non-polarized contribution in relation to the HH and to the VV channel. And here we have the results. So first thing we can say about this is that the non-polarized contribution for the HH channel is always higher than the one to the VV channel. And other important results here regarding the internal wave crests and troughs is that the internal wave, the non-polarized contribution to the internal wave crests is always higher than the one to the internal wave troughs. So we can see very clearly this in the graphics. So we have done a second experiment considering the wind direction. And in order to do it, we have calculated this term here, the delta NEP. And the delta NEP is the non-polarized contributions of the crests by the non-polarized contributions of the troughs. And we have analyzed the NEP according to the azimuth angle and to the beta angle. The azimuth angle is the angle between the rudder look direction and the wind direction, and the beta angle is the angle between the internal wave traveling direction and the wind direction. And here, analyze the first case, we cannot see any clearly dependence of the delta NEP according to the azimuth angle. And this can be because our data set's limited only to 10 images. Maybe if we could have access to a larger data set, we could start to see some dependence as appointed for previous authors. Okay, but however, here in the second case, we can see a very clearly dependence of the delta NEP according to the beta angle, that is to the internal wave traveling direction, where we have higher delta NEP values when the internal wave traveling direction is against the wind direction. And we found lower values of delta NEP when the internal wave traveling direction is perpendicular to the wind direction. And so we have done a third experiment considering the second order descriptors. And so we have calculated the Freeman-Durden decomposition.
That's 1 minute.
Okay. But in this case, we have analyzed only the volumetric component. So we have used the transects that I said before in order to understand if the internal wave could in some point model also the volumetric component. And so we analyzed all the transects, but we could not have some clearly pattern because in some cases we have a very clear modulation of the volumetric component by the internal waves, but in other cases, we could not see this clear modulation. And so we try to understand why this, and for that, we have taken the maximum value of modulation for each transect, and we have also plotted versus the beta angle, that is considering the internal wave traveling direction and the wind direction. And also in this case, we could have, we could see some pattern between both, because we have maximum higher modulations when the internal wave traveling direction is against the wind directions, and we have lower modulations when the internal wave traveling directions is perpendicular to the wind directions. Like here in the graphic, in these points here, where we have no modulation at all. So this result is very similar to the result we could find here for the delta NEP according to the beta angle. Okay, so as conclusion, we can say first that the non-Bragg scattering mechanisms have a non-negligible impact, even at L-band, mainly under the influence of surface current strain in internal wave crests, and their contribution can reach up to 48% until 56% of the total backscattering in case of surface current gradients owing to internal waves. And both AIT and VV non-polarized contribution associated to the internal wave crests is always larger than the one due to the troughs. And considering the beta angle, that is the internal wave traveling direction, the minimum and maximum contribution of the non-Bragg scattering with respect to the total normalized radar cross-section occur in downwind and upwind direction respectively. And also similar results apply for the modulation of the volume scattering component with respect to the beta angle. So thank you so much. And do you have some questions?